problems of shunt we will discuss. So we have already seen that in galvanometer, if I am connecting a shunt resistance, then some part of the current will go in the shunt, and whatever galvanometer requires for full scale deflection, that will pass in galvanometer. So I can say that if total current is I, then this current is getting divided into two parts. This we have already discussed in the working of ammeter. Now here what we have to discuss, suppose he says that in a galvanometer, a shunt used, shunt of say 6 ohm reduces the deflection to half, or reduces the deflection to say, I can say 1/3 of original value. That means the current has increased 3 times. So then I can find the value of galvanometer resistance by using Ig upon I is equal to S upon S plus G. Ig upon I is 1/3 and S is 6 ohm, so this is 6 plus G. So that should give me G is equal to 12 ohm. Now this G is original resistance of galvanometer, which I have now shunted by a resistance of 6 ohm. Now further what he is asking, what further shunt is required to make its deflection half of the new value. Whatever deflection has been obtained after the first shunt, that again should be reduced to half. So now what I can do here is, I can find the G parallel S, that will be new resistance of galvanometer G dash. So that will be 12 parallel 6, that is equal to 4 ohm. So then I can use this G dash in Ig upon I formula. So Ig upon I is half. We is saying it is reduce the deflection to half. This is what we say here, to half. So then Ig upon I will be half is equal to G dash, that is 4 upon S plus, half is equal to S upon S plus G dash. So that half is equal to, now this S which I will get, I can call it as S dash. So S dash upon S dash plus G dash is of what I calculated is 4. So if I cross multiply, then I should get S dash is equal to 4. In fact, these many calculations you don't have to do, because when he is asking that the deflection falls to half, then the galvanometer resistance and shunt resistance will be equal. So directly I could have used S dash is equal to 4, because he is asking the shunt to make the deflection equal to half of the existing value. So this is one question which can be asked in galvanometer. Another question which can be asked for galvanometer is that the deflection in a galvanometer falls. The deflection in a galvanometer falls to say 1/5 of its original value. When it is shunted by say a resistance of 4 ohm. to what value will the deflection fall? If a further shunt of 2 ohm is used, this is what the question is. Now here again we have to follow the same procedure, that Ig upon I will be 1 upon 5 and S is given as 4. So 4 and this is 4 plus G. So I can calculate the original resistance of the galvanometer, that will be 4 plus G is equal to 20, so G will be 16 ohm. So now G dash will be 16 parallel 4. So that should be 16 into 4, that is 64 upon 16 plus 4, that is 20. 4 ones are 4 5. So I will keep it 16 by 5. Now this G dash I have. Now what I want to find is the value of shunt. No, I want to find the value of Ig upon I. So that is what he is asking. Now when he used the first shunt, the galvanometer deflection became 1/5. So then I can use S, that is 2 ohm. I can write the formula. S is equal to Ig into G upon I minus Ig. Now these all are second values, so I can take them as dash values. So S dash is equal to Ig dash into G dash upon I minus Ig dash. So S dash is using the second shunt is of 2 ohm. Ig dash will be 1/5, so 5 times. G dash I have calculated 16 upon 5 divided by I minus 5 Ig. So this 5 and 5 should get cancelled, this 2 ones are and 2 8s are should give me 16. So I can bring this I minus Ig on the left hand side, so it will become I is equal to 13 Ig or 1 by 13 is equal to Ig upon I. So this will be the new deflection in the galvanometer. So these are the two questions that we still had to discuss regarding the shunt resistance part. Now there are a few questions which can be asked on conversion of galvanometer into voltmeter. The voltmeter conversion also we have discussed, but there are some circuitry questions which we can discuss. Like if you have a galvanometer, here it is a resistance of say 400 ohm. This is another resistance of 500 ohm and this is 2000 ohm. Galvanometer resistance is 2000 ohm and here he is putting a supply of say 240 volt. Now what will be the galvanometer reading? Now as it is, this is 2000 parallel 500, so that makes it 400. 2000 parallel 500 is 400 and 400 here and 400 here. This total resistance parallel combination will become 400. So 400 and 400, that means voltage should be equally divided. So galvanometer will show me 120 volt because 50-50 divided, that is 120. So in series, because voltage is getting divided, I should get my answer as 120 volt. Now the same question what he says is, suppose he is giving you a diagram like this. Here there is resistance, here there is resistance, here there is a supply. This resistance is 200 ohm, this resistance is say 300 ohm. Galvanometer is put here, voltage is 40. When it is connected to 200 it reads 40. What will it read when connected to 300? What will voltmeter read when connected across 300 ohm resistance? Now obviously the number of times the resistance is increasing. Even though he is giving resistance of galvanometer here as say 800 ohm, that doesn't make any difference. The number of times which the resistance increases, 200 is giving me 40 volt and 300 is giving me how much? So here I can easily say that this is increasing 1.5 times. So voltage will also increase 1.5 times. 40 into 1.5 should give me 60 volt. So easily I should be able to get the answer, that is 60 volt will be the voltage which we will get across when the galvanometer or the voltmeter is connected across the 300 ohm resistance. So these are voltmeter questions. Now you can get ideal voltmeter also. When the resistance is not given, that means it's an ideal voltmeter, its resistance is infinite. So that case also you can proceed in a similar way in which we have done in the last question. Now what one type of question is commonly asked is that resistance and then you have an ammeter and this ammeter reads 4 ampere, resistance is R, and here there is a voltmeter. A voltmeter reads suppose 24 volt. Now he is asking me what is the value of resistance. Now commonly what happens here is we think R is equal to V upon I. So 24 upon 4 should give me 6 ohm, but that's not the case here. Because what's happening is this 24 volt is voltage across ammeter plus resistance. So in this question he is just trying to check whether you have that concept of voltage across ammeter or not. So 24 volt is resistance voltage plus ammeter voltage. So that means across the resistance the voltage should be less than 24 upon current is 4. So my answer should be less than 6 ohm. So this is again another type of property of ammeter which he is checking with us. Then another question which he can give in the same cases. Here you have like this and then across the ammeter first, then resistance. Then he gives here voltages, voltmeter here, resistance over here R. This ammeter he is saying 4 ampere. And this voltage again he is saying 24 volts. So what is the value of resistance? Now in this case R is equal to 24 volt is there across resistance, no doubt about that. But the current in the resistance is not 4 ampere because some current will pass here also. Some current, very small current will pass in the voltmeter. So the current in the resistance is less than 4 ampere. So 24 upon less than 4, that means the answer should be more than 6 ohm. So here you have less than 6 ohm and the other one you have more than 6 ohm. So this is all what we have about the ammeter and the voltmeter questions which can be asked. This part we have discussed. Now we have another important discussion, that is the Ampere's law. Now what we have studied in so far is the Biot and the Savart law. Now in Biot and Savart law what we need is the integration of dV we have taken, that was mu naught upon 4 pi IDH and beta upon R square. Now that law is applicable at all case situations, but it's little lengthy to apply. Comparatively a simpler law is the Ampere's circuital law. Now according to this Ampere's circuital law, the line integral of magnetic induction over a closed loop. Suppose you have a closed loop, then you have to take the line integral of magnetic induction over that closed loop. The line integral of magnetic induction over a closed loop is equal to magnetic permeability of free space times the current enclosed by the loop. Current enclosed by the loop. This is what I can call as the Ampere's circuital law. But in that case, you have a loop carrying current I. This is a conductor which is carrying current I. I want to find magnetic induction at point P. Now this point P is at a distance of say small a from the conductor. Then what I can do here is I can form a loop. So this is the loop which is around the conductor, something like this. Suppose you have this is the conductor, then you form the loop like this around the conductor. You can see this loop like this here. So this is the loop which is formed around the conductor, and on this loop itself I have to take the line element, that is dl. Now once I take the element there, I know that around the conductor the magnetic induction by right hand rule here, this magnetic induction is going to come around in the loop. So the direction of dl and the direction of b are one and the same. So my mathematical format of Ampere's law becomes b dot dl, that is b dot dl means the line integral which I have written over here. So b dot dl is b dl cos theta, but theta is 0. So cos of 0 is 1. So b into dl is equal to mu naught into summation of all the currents which are enclosed by the loop is I. So then I can write b into, now dl, I take integration of dl, that is mu naught into I. So integration of dl, if I integrate all these dl's, I should get the circumference, that is 2 pi a. If I am calling this distance as a, then dl should be 2 pi a. So it will be mu naught upon 2 pi into I upon a. This is same what we have obtained for straight conductor, that is infinitely long straight conductor. So this is what you can call as Ampere's law. Now Ampere's law, what type of questions you can expect? Simple questions are there. You have a conductor which is suppose say like this. This is carrying current 4 ampere. There is another conductor which is carrying current of say 6 ampere, and then the third one is carrying a current of say 8 ampere. You can take any currents, that's immaterial. Now what he does is, he gives you a loop. Now you have to check which loop he is giving. Suppose he gives you a loop something like this. Then he asks you to tell what is the magnetic induction over the closed loop. So then I can write it is b dot dl, that is line integral, is equal to mu 0 times I. Now I consider upward going current as positive and downward current as negative, so that makes it 4 minus 6, that is minus 2 mu naught. So then he is asking me to find this value. The question is to find this value, so my answer is minus 2 mu naught. Now if he would have asked me for this loop, then this is minus 6, this is plus 8, so my answer would have been 2 mu naught. So that is obvious. So that is one question which he can ask regarding Ampere's circuital law. Now this Ampere's circuital law is used to find magnetic induction inside a solenoid. So solenoid is something which is like a cylinder having number of turns of a coil. So that is what I can call as a solenoid. Now you consider that suppose you have a solenoid of something like this. This is a solenoid having number of turns, that is n. The length of the solenoid is L, and I am passing current I inside the solenoid. Then what I can say is the magnetic induction inside the solenoid is uniform. Inside the solenoid, the magnetic induction is uniform. That means it is constant at all places. And then he asked me what is the value of that magnetic induction. So then I can write B is equal to mu naught into N into I, where small n is not number of turns, but it is number of turns per unit length. So this is what magnetic induction inside the solenoid is. Now this value is going to remain uniform at all points as far as inside part is concerned. Outside the solenoid it is 0, and if you take any point outside the solenoid it is 0, and if you take end points, then there are two ends, so at any end it will be mu naught Ni upon 2. So these are the equations regarding solenoid. Now there will be direct substitution questions. Now one thing what he can do in this here is, he can put a metallic plate like this. It's a rectangular plate, or it may be circular also. There is nothing significant in that. Now since this plate is inserted inside the solenoid like this, something like this, yeah, and the area of the plate is more than the area of the solenoid, the area of cross section of the solenoid, suppose I call this as the diameter of the solenoid, that is D, then area of cross section of the solenoid will be area of cross section will be pi d square upon 4, or you can take pi r square also. Now this area of cross section is small and the area of the plate is large, so area of plate is greater than area of cross section. Then what I have to do is flux associated with the plate, will be B of solenoid into area of cross section. We don't take the bigger area, we always take the smaller area in this case. So B solenoid into area of cross section. Or in that other case, if the area of cross section is more, then you take area of plate, because that will be the smaller area in that case. So whichever is smaller, we always consider that particular area for our calculations. So I hope you followed this particular part, that what area we have to consider while calculating the magnetic flux associated with the plate which